So there's a few things we need to understand about thermochemical equations and their delta H of reaction. The reality of it is that each individual thermochemical equation is specific for both its quantity of substance present, the direction the reaction is going, okay, and of course the states of the matter that's in those reactions. Okay, so what do I mean by that? If we go ahead and we look at this first example here, okay, so we're basing our comparisons below on this initial equation. Okay, so notice this equation, 2 moles of H2 plus a mole of oxygen give you 2 moles of H2O. The enthalpy of that thermochemical equation is going to be corresponding to the negative 483.6 kilojoules. Now, what I want you to notice is what we've done to this equation is we've multiplied all of it through by 2. Okay, so the reality of it is that the delta H of this thermochemical equation is going to be double the original amount because we've doubled the quantity of reactants present. Okay, so if you have more of something, it's going to be able to either release or gain more heat than if you only had half of that quantity. Okay, so if I double something, if I triple something, if I quadruple it, your delta H value is going to change proportionally. Okay, same thing would be true if you divided through, okay, or if you halved it, right? If I halved this equation here, then obviously my delta H value would be halved. Okay, now also remember that your delta H of reaction for your thermochemical equation is going to be proportional to the direction of the reaction. So if I took this reaction here and I reversed it, so flipped it over, the reality of it is that my sign of my reaction, my delta H of reaction, is also going to change. So in this case, I've flipped this. Okay, so notice that the delta H value that I now have for this reaction is positive. Okay, and of course, guys, the reality of it is that the delta H of your reaction is going to depend on the states of your reactants and products. Remember, it requires heat in order to go from a liquid to a gas. Okay, so we can't treat a gaseous molecule of water the same as a liquid molecule of water. Okay, so make sure that you're paying attention to those states of matter because they are important. Hess's law states that if a reaction is carried out in a series of steps, that the delta H for the overall reaction is going to equal the sum of all the individual enthalpy values for each of the individual steps. Now the reason why this works is because enthalpy is a state function, so the route that you take to get your overall enthalpy value for your reaction doesn't really matter. The only thing that matters is the initial and final states. Hess's law is also really useful, but because we are able to determine the enthalpy values for certain reactions, and we have lots of tabulated data that we'll be using. Now, what ends up happening is we can take those more easily determined delta H values from those simpler experimental processes and use them to obtain or determine more difficult to figure out or more difficult to measure reaction types. So let's go ahead and let's look at Hess's law in practice here. I want you guys to notice that we have two reactions here. They both have specific enthalpic values. Okay, and basically these two reactions are connected in the fact that we can utilize them to figure out the overall enthalpy change of this process. Okay, now it might be difficult for you to see initially, but if you look at this combustion reaction, basically what we have here is we have methane that's being reacted with oxygen to produce CO2 and H2O. Notice the H2O here is in the gaseous state. In the reaction that we have down here, notice that we have H2O in the liquid state. So in this situation, the reaction here and here are not exactly the same. Okay, so in order to figure out this reaction, I'm going to take this thermochemical equation and its enthalpic value and utilize Hess's law along with this thermochemical equation and its enthalpic value to find the enthalpic value of this process. Okay, so what I'm going to do is I'm going to take these two equations and I'm going to sum them. Okay, notice that all my reactants get carried down here. all of my products get carried down here. And what I'm going to do is I'm going to simplify in any situations that I can. And what I want you to notice is that your gaseous H2O, your 2 moles of gaseous H2O show up on both sides, so both of those will cancel, leaving you with this remaining equation. Okay? Now, the overall equation that I want to calculate for is able to be obtained from these two thermochemical equations. And then what I can do is I can sum the enthalpic values for the individual thermochemical steps that I used to obtain this equation. Okay, so I add these two together, and that's going to give me 890 kilojoules for my delta H. So with Hess's law, as long as our thermochemical equations, our individual pieces, can sum to the overall equation that we're looking for, we will be able to utilize this approach to solve for the enthalpy value of a specific process. So if I didn't have this information in a table, I could use these two to solve for it. All right, now, please make sure that you guys are paying attention to the states of matter. Okay, notice this is in the gaseous state and this is in the gaseous state. These two can cancel each other because they're in the same state. In that same vein, okay, the H2O here cannot be canceled because it's in the liquid state. Okay, so the states of matter matter, so make sure you're paying attention to that when you do your calculations. Okay, so let's look at this example that they've given us here. It says to determine the heat of reaction for this reaction here below. Okay, I have 4 moles of NH3 in the gaseous state plus 5 moles of O2 gaseous state, giving me 4 moles of NO in its gaseous state and 6 moles of H2O in its gaseous state. Now, they've given me a set of reactions. Okay, this is a completely appropriate way to solve for this, and I need to utilize these 3 equations and these 3 delta H values in order to get the overall equation. So remember, I'm going to need these equations to sum to this equation in order to get the delta H of reaction for this specific example. So let's go ahead and let's look at how we're going to do this. Okay, so when we're dealing with these problems, we're always going to be paying attention to what our overall goal is. Remember, we need to modify these equations so that the overall equation will be what we get when we sum the above. So if we take a look at these equations, go ahead and let's look at this first one. Okay, notice NH3 is on the right-hand side. Okay, NH3 in this thermochemical equation is a product. However, NH3 is a reactant in this situation. NH3 doesn't show up in any of the other 2 thermochemical equations provided, so we know that this equation is going to need to be flipped. Okay, so if we reverse this equation, remember, if we reverse the equation, the sign is going to change. Okay, so that's the first thing to think about. Now, if we also look at the way that this equation is balanced, how many moles of NH3 do we have here? We have 2, but we actually need 4. So in addition to flipping this equation, we're also going to have to multiply through by 2. So all of the coefficients here are going to be doubled, as well as the delta H value is going to be doubled. So if we look at what we've done here, we've doubled the coefficients. Okay, so we've multiplied everything by 2, and we've also flipped it. Notice it's the reverse reaction of what we have here. So if we come over here to our delta H value, we will notice that our sign is now positive, and we've doubled the value of the delta H. Okay, so if we go down and we look at this next equation here, okay, the next thermochemical equation provided, notice we have N2 and O2. Okay, O2 is on the left-hand side, so that looks like it's okay. But NO is on the product side. If we look at our goal equation, notice that the NO is on the right-hand side. So this equation doesn't need to be flipped. Okay, so the sign of our delta H here is not going to be changed. Now, if we look at the coefficient here, though, NO has a 4 in front of it. The NO for this equation only has a 2. So we know that we're going to need to multiply this equation's coefficients as well as its delta H by 2. So if you go down here, notice we've multiplied everything through by 2 to get the appropriate values. and we've multiplied the delta H by 2 to give us our new delta H value that corresponds to the coefficients of that specific equation. Okay, and then this last equation that we need to look at, notice H2O is on the right-hand side, O2 is on the left-hand side. Everything seems to be in the appropriate location, so no flipping is necessary. However, if we look at the coefficient here for H2O, it's only 2. Notice we need a 6 up here, so we need to multiply all the coefficients here by 3. So we've multiplied everything through by 3, and we've also multiplied our delta H value by 3 to give us our overall new delta H for this specific equation. So now that we've flipped and multiplied all of the equations provided to match up with this equation, we then need to do a summation process. So if we have all of these once again lined up and we sum all the reactants on the left hand side and write them out, and all the products on the right hand side and write them out, we can then utilize this equation to see if we get our overall equation that's being desired. So the way we figure that out is once we've established our reactants and products on the right hand side, we cancel anything that shows up on both sides. Okay, so I have 6 moles of gaseous hydrogen gas on both the reactants and product side. Okay, I have 2 moles of nitrogen gas on both the reactants and product side, and that leaves us with the equation below. Okay, and this equation matches the overall equation that they are wanting us to have and wanting us to solve for. So now that we have this overall equation and the thermochemical equations that were provided do in fact sum to the overall equation we're looking for, we can now use the delta H values, the summation of all of these that we've calculated, to give us our new delta H for this specific reaction. Okay, so basically we've done all the flipping earlier on that we discussed and looked at on our last slide. We then cancel everything out and make sure that it matches the overall equation of the equation that they're asking for. Remember to pay attention to the states of matter. If they're not in the same phase, if they're not gaseous when they're supposed to be gaseous, then you don't actually have the equation that you need. Okay, so there's something missing. And once we've solved and shown that we can get this overall equation from these individual thermochemical equation pieces, we can sum the stepwise delta H values to give us the overall delta H of this specific reaction. A question that may come around with this type of problem is also, is this reaction exothermic or endothermic? And if you look at the sign of your delta H, assuming this is a constant pressure, your delta H and your Q are proportional, and because of that fact, the sign of delta H here will be negative, so the sign of Q will also be negative. A negative Q is going to imply that you have an exothermic reaction. So just make sure that you're paying attention to the pieces that they give you. Make sure that the coefficients of your products match up. Make sure that if you flip something, you also flip the sign. If you multiply through by a coefficient, your delta H has to be multiplied through by the coefficient. All of the equations that you're utilizing must give you the overall equation that you're solving for, and then you can add the delta H values from those individual steps to give you the overall delta H for the specific reaction.